Thank you so much, Simon. Thank you very much for the opportunity. And as Simon was telling you, I'm going to talk about operando photovoltaics and microscopic evaluation of the recombination center in a halide perovskite-based solar cell. So it's a very big title, but what I actually want you to take here is the understanding of how can operando characterization of multi-layer systems such as a solar cell can answer fundamental questions. The second thing that I would like you to take is what is the role of the recombination center in halide perovskite? And both of those questions are going to lead me to answer a big question, which where are the power conversion losses in a halide perovskite solar cell? And if you can think about your daily life, this is not such a big question. Whenever you try to tweak your device to make a new perovskite or to add another layer, you can get a batch that doesn't work. You can get some of the cells which do not work, or even all the concept that you try to apply with some fancy hypothesis is not giving you a high performance. And usually we would like to present and also publish cells that giving us high performance. So in order to answer those questions, to understand where we have the losses, I'm going to briefly going through the photovoltaic effect and break it in 3 steps and try to evaluate each of the steps where we can have or where is the likelihood to get power conversion losses, and try to approach the specific spots that can be problematic. So the photovoltaic process can be broken into 3 things. One is the light absorption that creates excitation. The second process is the separation of the electron and the holes to be free carriers. And the third process will be the collection of those holes and electrons. The common way that I think most of the paper already today presented to evaluate the light absorbent process is to measure the absorption coefficient. I'm showing here one figure, but I guess many people have many papers show those figures of a comparison of two well-known technologies such as the crystalline silicon and the gallium arsenide comparing to methylammonium lead iodide. And as you can see from the absorption coefficient, first of all, the methylammonium iodide is well tuned to the optimum of the solar spectra, which is somewhere around here. But also you're getting higher values for the methylammonium iodide in terms of the absorption coefficient for a light, comparing to the crystalline silicon and the gallium arsenide. This is why we have very thin layers. And it's basically those materials, this is what's so magic about them and why many people around the world decided to learn them during the last 10 years. So it's amazing material to absorb light. The second process, in order to evaluate how good is the charge separation, we need to measure the quantum yield, how much what is the quantity of each excitation resolved to be separate free carriers. And again, this is a well-common characterization, and I'm showing only one figure from Sutafella paper a few years ago when she measured a different methylammonium lead halide composition, and she showed that the quantum efficiency of those cells, of those layers, sorry for the layer, is almost 30%. And this is basically the thermodynamic limit for those materials, and it's almost as good as it gets. So we're not expecting that we have charge separation issues in our device later, but those are only measured on films. And the last a process that usually get less attention or have a special papers that characterize the efficiency is the charge collection. Once we already have free carriers, we need to understand how much time it will take them before they will decay and how fast they will can move in the layer. And this is basically the mobility lifetime product, which can evaluate us the current collection. But as much as I understand, there is, I think, more than 6 or 7 techniques to characterize each of them separately, such as, for example, PL for lifetime or SSPG for mobility. But all of those techniques usually use the film itself or a special symmetrical contacts to evaluate those properties. So you're taking your perovskite itself and measure what is the lifetime, for example, for material monomer iodine. Usually it's a few hundreds or 2 microns a second. But I can argue that this is not the right way to do it, and I will try to convince you why. Measurements that different work that I was doing a few years ago, try to evaluate the Fermi position and the doping level of different perovskite. And what we usually do, we basically spin coat our layer on gold. And if you can, oh, maybe I should use a laser so it will be easier. So you can see nicely that when you spin coat your formaldehyde methylamine cesium, or shortly I will call it mixed cation lead bromide, on a gold substrate, you're getting highly p-type materials, the Fermi very close to the valence band. However, and which was repeatable, and we were very happy about the results to learn about this junction. But one day we ran out of gold, and we spin coated it on aluminum because it was flat on silicon, and the results was different. We tried to think maybe the aluminum was oxidized, so there was some problem. Repeat the results. It was just the same results regarding a different work function, which was close to the mid gap. And then we decided to use variation of different substrate, and you can see the work function of the substrate in the x-axis, and you can see the measured perovskite work function in the y-axis. And to some extent, we can follow the work function of the perovskite of the substrate for our perovskite. And this phenomena is basically can be explained when the depletion layer of the layer itself is not wide enough in order to see the carriers for the perovskite. And basically what we can, or in simple words, the perovskite layer was transparent in terms of the work function. We measured the substrate itself. And this was published in a different work, but why do I tell you this? Because it do matter what are the selective contacts that we're using. A lifetime in a perovskite that sit on a gold is a different than lifetime that sit on a different layer. And in order to evaluate the mobility life product in an accurate way that will present what is going on in your solar cell, you need to find a measurement that measure it in a device configuration and give you the real picture. Okay, so here come the presentation of the technique that I used. I used the electron beam induced current. This is a name of a setup, but basically what I'm using here is a microscope, SEM. And I will go through the explanation of the scheme later, but let's go with to give you some intuition how it works. So I'm taking my solar cell and I'm cleave it to half, and I'm mounted here on an isolated stage. On top of it, I will put 2 probes on the high and the low parts of the cell in order to be able to collect the current. Okay, so now my sample is ready. I'm inserted it to the SEM. And what the SEM can do, it's first will give me a secondary electron image, which what usually SEM is doing. But also I can use the electron beam as a very fine probe that can electronically excite a hole and electron. Just because I'm bombarding my sample with electron, I can get local excitation, and I can collect the current if there is current, similarly to where I can collecting the secondary electron. So let's think about a semiconductor where you have a p-n junction, and you start to excite very far from the junction itself where there is no built-in. there will be an electron and a hole that will be excited. The likelihood for the electron to go to the electrode is very high. However, the likelihood of the hole to diffuse through an N-type material and to go all the way to the other side of the electrode is very small, and we're expecting very low currents. As we continue scanning and getting very close to the space charge region, we basically expecting that because there is a built-in potential, the drift force will push the two carriers to their contacts, and we can collecting the current very easily. And if we can try to draw a profile of the intensity of the current as a function of the position inside the PN junction, we can expect very low current farther from the space charge region. And as we getting closer to the area where there is a built-in voltage, we should see more and more carriers being collected, and the intensity of the current is increasing until the point that we're getting to the space charge region. And there we're expecting kind of a plateau, because every excitation should end up with a current collection, And you can think about it symmetrically or with different slope for the p-type, because again, here the electron that excited here should go through all the way to the other electron. So this is theoretically what I'm expecting. So back to the scheme, because I promised to explain it. This is my sample, and I'm collecting the current and amplified it. I can also use a beam blanker and look into the signal to have more accurate, but it doesn't necessarily have to work like this. And on the same time, I'm getting the secondary image. And then I can getting basically two images simultaneously from the same scan of the beam. And here I'm showing a cross-section of a methylammonium lead iodide cell, where I have the gold as a front contact, the spirometad, methylammonium lead iodide, mesoporous titania, and dense titanium. And here is the EBIC picture. Basically, you show me where I collected current in my cross-section. Very nice, very simple. It's taking half an hour, and it's very straightforward to understand how is my solar cell work. What can I extract from those images? I can learn about how the electric field evolved in the cell. I can learn about the minority carrier's diffusion length, which is the square root of the mobility lifetime product. I can also can evaluate the defect or the current losses, and learn where the width of the space charge region. So all of those properties is extremely important properties in semiconductors understanding of the photovoltaic process, and they all can be accumulated from one measurement. So let's look a bit on data. On the time, okay, I have 5 minutes. Let's look a bit on the data. So for the methylammonium lead iodide, as I showed before, this is a bit worse picture, but it's very beautiful cell. If I'm not mistaken, made in Oxford, most of it is iodide. And what we can see here is the same plateau that I showed you before, but it's kind of going through all the perovskite layers. So this is the perovskite layer, and we have the width of the space charge region through all the semiconductor. And in this case, basically, we can say that we have a PIN junction. This is not new news. Everybody knows that the methylammonium iodide based are PIN junction. You see the junction for close to the selective contact, or drop, sorry, close to the titania and the spirometad. And we can say that here we don't have any issue of diffusivity or current collector, because we're getting from all our perovskite uniform current. This is amazing, and this is why people want to work on iodide. So the iodide is not our story. Let's look on the bromide. So the bromide is showing here 2 cases. One is for the methylammonium lead bromide, and one for the mixed cation lead bromide. Those are results published a while ago, and they show that the junction is very close to the TiO2. Okay, so as I showed before, the bromide tend to be p-type because it's getting the work function from the gold, and the junction fall very close to the electron transport layer, and the diffusion length found to be 50 nanometers. In the mixed cation, as we know that we're giving a higher efficiency, the junction is, or the diffusion length is order of magnitude, almost order of magnitude higher. And we can see that we basically get a current almost through all the perovskite. So it's still PN junction, but we can take this decay and try to estimate what will be the diffusion length, which come out more or less close to the layer, the thickness of the layer. And now we stop for 1 second and we say, okay, there is, when we use the electron beam current, we locally excite our carriers. But what if we, in a solar cell itself, I'm illuminating all the sample and then the population of the bed changing just because the radiation is different? Could it affect, in a real case of solar cell, the diffusion length of the carriers? And the work of CADM also tried to tackle that, and they found that they basically getting higher diffusion length after they illuminate the cell. This work was also done with a group in Berlin of Daniela Boas. But I get a different results when I measure it. When I use the mixed cation, I basically get a very nice confined junction after illumination. And I know that those cells are work better. And the question is why? Why sometimes when I'm illuminating, I'm changing, or I can able to modify the diffusion length. So back to the equations, trying to understand what's going on there with the help of Yitzhak Wahlberg, professor in Hebrew University, and also Igal Levin, that now is in Berlin. We try to solve numerically 3 equations, or put all the numbers together. We assume that we have, or we know that we have charge and neutrality in our system, or also not a charge. We wrote the rate equation for the generation meaning how much light do I, or how much carrier do I adding when I illuminating, and also the lifetime definition. One assumption we done is marked in red over here, that we have one effective defect state. We don't know where it's located, but it could be that there will be some trap filling during the illumination process. And solving this numerical question, we came up with the numbers. So this is only a model and only theoretical. But what I'm presenting here in the x-axis is the amount of carriers that are generated as function of time, which is like my illumination. The y-axis representing the diffusion length of the minority and the majority carriers, depends on dashed or full line. And I assume for each time that I send it to iteration, a different amount of defects that located in my state, in my defect state. And what I found here is that whenever I have the majority carriers, and this is very low intensity. So whenever I have a lower illumination, basically, as I adding more carriers, the diffusion length of the minority carriers always decay, always going down. And when I have, and when we look on the minority carriers, in the beginning, adding such a low amount of carriers, 10 to 12, 14, does not change much the diffusion length of those minority carriers. At some point, when I'm adding enough carriers, they can actually fill the traps, and then I'm getting some increase of the diffusion length artificially. And once I going through this threshold, it will also reduce as the majority carrier life, and as the majority carrier. And if we try to look back on our EBIC image, so basically we saw for the methylammonium lead iodide increase after illumination. So it's somewhere over here. as you can see, and the yellow shade over here representing the area where I illuminate the intensity of illumination that I use in the EBIC. So it's somewhere over here, and we assume that we have 10 to the 14 to the cubic centimeter defects for our layers. And for the mixed cation methyl bromide, we get a decrease, which means that we already in this regime of the slope where the diffusion level is going down as we add light. And it hints us that we have less than 10 to 13 defect per cubic centimeter. And this is why this cell is operating better. And the level or those quantities of defects is very low. And if you can think about any other techniques that can assess, I think 10 to the 5 less than what you have in the valence band, less carriers, it's very difficult. Usually the sensitivity of the UPS and many other techniques is like 3 orders of magnitude below the population. And this is very nice to get some data out of it. And to conclude, it's very important to do an operand or to measure those properties in a cell configuration in order to get accurate values, because the contact do matter and do affecting the properties. And unlike our intuition, once we illuminating or adding more carriers for less defect material, we should expect a lower diffusion length. Simon asked me also, I don't know if you have like 1 minute briefly, I will mention that we done it for many cells, and it was very easy to see that those are the same batch cells, that sometimes there is just a cell that the quality of the Perovskite itself is not as good, and we barely getting current through this materials. And you can see very nicely the defects. It's not like you done something wrong. It's just like those spots specifically didn't give nice cells. We also try to check if the grain boundaries can affect, because you saw that like I can mimic the structure of the crack in my EBIC cells. So this is a different phenomenon, but once I shave or make the cross-section flat, I don't see any contribution for the grain boundaries. They're not contributing or not reducing the efficiency of the cell. Another thing that usually people don't show, but beam damage do existing, and after scanning a few times, you see, so the profile doesn't change. I don't get a PN, if I start from PIN, I'm not getting PN junction. It stays still PIN, but the reduction of the current that I collect after beam damaging the surface, affecting the measurement itself. So with that, I would like to thank you for your listening, and also the NGSE for giving me the opportunity to give a talk, and for my collaborators. And yeah, that's it, I guess.